Welcome back. In the last two talks, we built sensitivity, specificity, PPV, and NPV from the 2x2 table. These are powerful tools, but they have one practical limitation. Predictive values require you to know or estimate the prevalence in your specific population, and then recalculate every time you move to a new population. What if there was a way to express a test result strength that you could apply directly to any pretest probability without rebuilding the full table? That tool exists. It's called the likelihood ratio, and it's arguably the most elegant and flexible metric in all of diagnostic test interpretation. Likelihood ratios are tested heavily on the ACVPM exam, and they're the tool that experienced epidemiologists and evidence-based clinicians reach for when they want to think carefully about what a test result actually contributes to their probability estimate. This talk will make them completely approachable. Let's start with the core idea. A likelihood ratio tells you how much a test result shifts your probability of disease, expressed as a ratio of two probabilities. The positive likelihood ratio, LR+, asks how much more likely is a positive test result in a truly diseased animal compared to a truly healthy animal. If LR plus is 10, a positive result is 10 times more likely to come from a diseased animal than from a healthy one. That is a meaningful test. The negative likelihood ratio, LR minus, asks how much more likely is a negative test result in a truly diseased animal compared to a truly healthy one. This one is a little counterintuitive. We're asking about negative results in sick animals, which is the false negative rate. If LR minus is 0.05, a negative result is 20 times more likely to come from a truly healthy animal than a truly sick one. A very reassuring negative. The reference point is always 1. An LR of 1 means the result gives you no new information. A positive is equally likely in sick and healthy animals, so it does nothing to change your probability estimate. LR plus values greater than 1, and ideally much greater, mean a positive result increases the odds of disease. LR minus values less than 1, and ideally much less, mean a negative result decreases the odds. The formulas are built directly from sensitivity and specificity. LR plus equals sensitivity divided by 1 minus specificity. LR minus equals 1 minus sensitivity divided by specificity. Let's calculate some and see what they tell us. Let's calculate likelihood ratios for abdominal ultrasound used to evaluate for splenic hemangiosarcoma in dogs. We'll use sensitivity of 75% and specificity of 90% for this example. LR plus equals 0.75 divided by 1 minus 0.9, which is 0.75 divided by 0.1, which equals 7.5. LR minus equals 1 minus 0.75 divided by 0.9, which is 0.25 divided by 0.9, which equals approximately 0.28. Now let's interpret those numbers. LR plus of 7.5 means a positive ultrasound finding is 7.5 times more likely in a dog that truly has a hemangiosarcoma than in a dog that doesn't. That's a meaningful positive. It substantially raises your post-test probability, but it's not overwhelming. It doesn't mean a positive result equals diagnosis. It means the probability has moved significantly upward. LR minus of 0.28 means a negative ultrasound is only 0.28 times as likely in a dog with a hemangiosarcoma as in a dog without it. Equivalently, a negative ultrasound is about 3.6 times more likely in a truly unaffected dog. This substantially reduces the probability of hemangiosarcoma, but with a sensitivity of only 75%, a negative ultrasound does not rule it out. This is the quantification of the clinical teaching that ultrasound does not rule out hemangiosarcoma. And now you have the number that explains exactly how much weight to give a negative result. Practical interpretation guide for likelihood ratios that you can internalize and use at the bedside. For the positive likelihood ratio, values greater than 10 produce a large, often conclusive increase in post-test probability. These are the tests where a positive result is very meaningful. Values between 5 and 10 produce a moderate increase. Values between 2 and 5 produce a small but real increase. Values between 1 and 2 are barely worth noting. The test isn't adding much information with a positive result. For the negative likelihood ratio, values below 0.1 produce a large, often conclusive decrease in probability. These are the tests where a negative truly rules something out. Values between 0.1 and 0.2 produce a moderate decrease. Values between 0.2 and 0.5 produce a small decrease. Values between 0.5 and 1 are minimally useful. The practical shorthand: if LR plus is greater than 10 or LR minus is less than 0.1, you have a strong test for that direction. If both LRs are within the range of 0.5 to 2, the test is weak regardless of direction. Going back to our ultrasound example, LR plus of 7.5, moderate to strong positive, LR minus of 0.28, small decrease. This tells you that ultrasound is more useful when it's positive than when it's negative. A useful clinical insight that the sensitivity and specificity numbers alone don't communicate as cleanly. Now let's use a likelihood ratio to actually update a probability estimate. This is the full Bayesian updating process we introduced conceptually in Talk 1.2, now made quantitative. The key thing to understand is that likelihood ratios multiply odds, not probabilities. So we need to convert back and forth between the two. This is a three-step process. Step 1. Convert your pre-test probability to pre-test odds. If your pre-test probability is 30%, your pre-test odds are 0.3 divided by 1 minus 0.3, which is 0.3 divided by 0.7, which equals approximately 0.43. You can read this as for every 0.43 animals that have the disease, one animal does not. Roughly a 30-70 split expressed as a ratio. Step 2, multiply your pretest odds by the likelihood ratio. Post-test odds equals 0.43 times 7.5, which equals 3.21. Step 3, convert your post-test odds back to a probability. Post-test probability equals 3.21 divided by 1 plus 3.21, which is 3.21 divided by 4.21, which equals approximately 76%. So, a dog with a 30% pretest probability for splenic hemangiosarcoma with a positive ultrasound finding and a LR plus of 7.5 now has a post-test probability of approximately 76%. That is a clinically meaningful shift from possible to probable, driven by a single test result. If the ultrasound had been negative instead, you'd use LR minus of 0.28. Post-test odds would be 0.43 times 0.28 equals 0.12. Post-test probability equals 0.12 divided by 1.12 equals approximately 11%. The probability dropped from 30% to 11%, substantially reduced but not eliminated. You'd still want to monitor or consider further investigation. Three-step odds calculation feels cumbersome. The Fagan nomogram gives you the same answer graphically, no arithmetic required. It has three vertical axes, pre-test probability on the left, likelihood ratio in the middle, and post-test probability on the right. To use it, find your pre-test probability on the left axis. Find the relevant likelihood ratio, LR plus for a positive result, LR minus for a negative result, on the middle axis. Draw a straight line through both points and extend it to the right axis. Where it crosses is your post-test probability. In our hemangiosarcoma example, draw a line from 30% on the left through 7.5 on the middle axis. The line crosses the right axis at approximately 76%. Same answer as the calculation, no math needed. The Fagan nomogram is a practical bedside and exam tool. You won't always have time to do the full odds calculation, but if you have an LR and a pretest probability, you can sketch a nomogram quickly or use a printed version to get an approximate post-test probability in under 30 seconds. For the ACV-PM exam, knowing how to use it conceptually, even if you don't have a physical copy, demonstrates the kind of applied reasoning the exam rewards. At this point, you've now learned 4 test metrics: sensitivity, specificity, PPV, NPV, and likelihood ratios. A natural question is, which one do I use? The answer is they're complementary, not competing. Predictive values, PPV and NPV, are the most intuitive for communicating results to clients because they directly answer the question, Doc, does my animal have it? In terms of simple probabilities. But they're population specific. Every time you change the prevalence context, you need to recalculate. Likelihood ratios are population independent. They're fixed properties of the test result derived from sensitivity and specificity, and they can be applied to any pretest probability using the odds method or the Fagan nomogram. This makes them ideal for taking published test performance data and applying it to an individual patient whose pretest probability you've estimated from signalment, history, and exam. In practice, experienced clinicians and epidemiologists use likelihood ratios for their own reasoning, updating from pre-test to post-test probability, and then translate the result into plain language predictive terms when talking to clients. Both skills are tested on the ACV-PM exam, and both are genuinely useful in practice. Summary. LR plus equals sensitivity divided by 1 minus specificity. It tells you how much a positive result increases your odds of disease. LR minus equals 1 minus sensitivity divided by specificity. It tells you how much a negative result decreases your odds. An LR of 1 gives you nothing. LR plus above 10 or LR negative below 0.1 are strong results. You update probability by converting to odds, multiplying by the LR, and converting back. Or use the Fagan monogram to skip the arithmetic. LRs are portable across populations because they don't depend on prevalence, and LRs and predictive values answer complementary questions. Use both depending on the context. In the next talk, we'll put all of this together: sensitivity, specificity, predictive values, and likelihood ratios into the practical context of test sequencing strategies, spectrum bias, and the consequences of getting it wrong. Pause the video, read the scenarios, and try your hand at answering the questions. We'll then work through the questions and answers together. This example is based on the well-established clinical profile of the UCCR, a highly sensitive but poorly specific test, making it a perfect real-world application of likelihood ratio interpretation. Question 1. Calculate LR positive and LR negative. LR positive equals sensitivity divided by 1 minus specificity equals 0.99 divided by 1 minus 0.77 equals 0.99 divided by 0.23 equals 4.3. LR negative equals 1 minus sensitivity divided by specificity equals 1 minus 0.99 divided by 0.77 equals 0.01 divided by 0.77 equals 0.013. Question 2. Interpret LR positive of 4.3. This falls within the small increase range of 2 to 5. A positive UCCR modestly raises a probability of Cushing's, but it's not strongly confirmatory. LR negative of 0.013 is below 0.1, a large, often conclusive decrease. A negative UCCR is a powerful rule-out. This test is therefore best used for ruling out hyperadrenocorticism, not for ruling it in. This matches the established clinical teaching. The UCCR is a screening test that, when negative, essentially excludes Cushing's disease. When positive, it requires follow-up with a more specific test. Question 3. Update the probability with a negative result. Pretest probability equals 40%. Pretest odds equals 0.4 divided by 0.6 equals 0.667. Post-test odds equals 0.667 times 0.013 equals 0.0087. Post-test probability equals 0.0087 divided by 1 plus 0.0087 equals 0.0087 divided by 1.0087 equals approximately 86%. Approximately 0.86%, less than 1%. You tell the owner a negative UCCR result makes hyperadrenocorticism extremely unlikely. The probability has dropped from 40% to less than 1%. Assuming the clinical signs don't clearly point to another explanation that was being attributed to Cushing's, we can reasonably cross this off the differential list. You may want to reassess the original clinical picture. Question 4. No, the UCCR is not appropriate as a confirmatory test. With an LR positive of only 4.3 and a specificity of 77%, a positive UCCR leaves substantial room for false positives. Trilostane carries real risks: adrenal necrosis, hypocortisolemia, and should not be initiated based on a test with this level of false positive rate. A confirmatory test with high specificity, such as the low-dose dexamethasone suppression test or ACTH stimulation test, should be used before starting treatment. This illustrates spin in practice. You need a specific test to rule in disease before committing to a high-stakes treatment decision.